we're talking about enthalpy, where the question was, where the definition of enthalpy was, enthalpy is the sum of the internal energy and the product of pressure, and pressure and volume, and volume. So this, in a simple way, what they're trying to tell us is that this is my definition that I can just summarize from what I know, is to say that the enthalpy, by the way, is the symbol is HI, is H. That is enthalpy. Mostly we talk about it having change in enthalpy, so we put the delta there. So delta H, meaning change in enthalpy. But yeah, the symbol is H. So this H, enthalpy I, again, it is also heat. It is heat at constant pressure. Okay, we'll come back to that. Let me just finish what I'm doing here. So I'll say that this definition I, so sum of internal energy and product of pressure I and volume. So this can be just summarized by saying that it is the sum. It is the sum of internal energy and work. So it is the sum of the internal energy and work. So the sum of these two guys. So what I'm saying that enthalpy, which has a symbol H, enthalpy is equal to internal energy plus work. Okay, so I don't know, earlier on, I don't know if you learned this, but yeah, from this equation I, remember when you are calculating internal energy, we use this I. Internal energy is equal to, we have heat I, heat Q plus WI, Q plus W, heat times, heat plus time I, heat plus work I, heat plus work, where we know that heat is just, is heat I, and then work has a formula of it on by saying that work is negative P times VI, although sometimes they say delta V, meaning change in volume I, but yeah, this I, okay. So we have W is equal to that. So in this case, we can have Shani, what is that called? That is not enthalpy. That is internal energy. Internal energy is equal to Q minus PV. We have this formula. So at constant temperature, we say that Q is equal to the H. So sometimes enthalpy is just heat. It's just heat. Enthalpy is heat when it is at constant temperature. So what happens here? So that this changes now. So at constant temperature, so we can replace where there is QI, we replace H now, and then we make that H the subject to the formula. So where there was Q, since Q was heat I, where there was Q, I'll replace H minus PV. So if I replace H where there was Q, I've already replaced HI. So now let me make H the subject of formula. To make H the subject of formula, what I will do is that I will take this side, okay? I will take the negative PV this side. So it will become energy, internal energy, it's negative, so it becomes positive. PV is equal to H. So I've made H is equal to what? Delta E, which is internal energy, plus PV. So that's why the definition says that this is the sum of the internal energy and the product, since these two guys are multiplying, and the product of pressure and volume. Sometimes this volume, sometimes you find that it's written as this. It is written as delta H is equal to internal energy plus PV plus P delta V. So meaning sometimes the volume can change I, where delta V can be volume 2 minus volume 1 I. Right. Enthalpy can be is equal to QP. This is just heat times pressure. Heat times pressure. And again, which is equal to the same thing that we did. Enthalpy is what? Is a change in energy, the sum of energy plus the product of PVI, the product of P and V. So which is pressure times volume. So you can either use this to find enthalpy, you can either use to find enthalpy. And the last equation that you can ever deal with is the one which deals with enthalpy when you have 2 or 3 enthalpies. So we say that enthalpy, change in enthalpy is equal to enthalpy of the product, the product, what you get in the, this is for equation, an equation. Enthalpy of the product should be minus the enthalpy of the shani of the reactant. So this is another way of finding enthalpy. Enthalpy is equal to enthalpy of the product minus the enthalpy of the reactant. So meaning what has come out minus what was there. So if in this equation you find that your enthalpy turns out to be positive, after doing this, you find that your enthalpy is positive. So if it's positive, that means it has increased. Enthalpy, don't forget, whatever it is expressed in joules. And anything that's expressed in joules, that means it's the type of energy or form of energy. So meaning, if it's positive, that means meaning energy has been gained. You have gained energy. And if you have gained energy, that means it's what? Endothermic. That means it is endothermic. You have gained energy. So if enthalpy turns out to be negative, that means you have lost energy, and losing energy, that is exothermic, meaning heat or energy has gone out. We're given this example saying when 1 mole of methane is burnt at constant pressure, 890 kilojoules is released. Calculate the enthalpy change for a process in which 5.9 grams of methane is burnt. Okay, so in this question, let's first identify the terms, the important terms in this equation. So the important terms, we have when 1 mole of methane, so we have 1 mole of methane. That's one thing to take into consideration. 1 mole of methane is burnt. It is being burnt at constant pressure. I think everything here is important. Even burnt is important in this case. It might have been important, especially if they told us to write the equation. If they tell us to write the equation, we could have used the burnt. This burnt equation. This burnt could have been more important. Okay, so it's burnt, and what happened? This much is released. So this much energy which is released, we can say this is enthalpy. It is released. Don't forget, it is released. The releasing is also important. It is released. Okay, calculate the pressure. Okay, so that's now a calculator. So we're calculating the enthalpy, or we're calculating the enthalpy change for a process in which this much of methane is burnt. Okay, so let's start from the beginning. So to start with, we have methane there. They never gave us the formula for methane. So methane is written as CH4. CH4. That is methane. I've said 1 mole of methane. So 1 mole of methane. Since we don't know the grams, we can just say that whatever the number is called here, you guys. Yeah, that number there. That number, or we can say the one we use for more ratios. Yeah, that number. I don't know the name. Okay, so that number is what? It's 1 mole. 1 mole. It is 1. And then this, it is undergoing what? 1 mole of methane is burnt. So it is burnt. So if it's burnt, that means it is undergoing combustion. And combustion uses oxygen. Uses oxygen gas. So it is burnt. And then if it's burnt, it produces. They never told us what it produces. But just to predict, okay, I'll just predict myself to say that when methane is burnt, it will produce carbon dioxide and water, H2O. Yeah, please, if you find something else in the books that methane when it's burnt it produces this and that, and you find that it's wrong, I'm wrong, please don't forget. I'm just a first year. I'm also trying to learn things here. Okay, so we have that. Okay, so what do we know? What do we know from here? We know that this is the equation I. Should I balance it? Okay, let me try to balance it, but balancing, is it important? Okay, it's not important in this equation, but yeah, just to balance it. If I can balance it, I've seen that this side there are 4 h's, there are 4 h's. If I have to make this one 4, I have to put a 2 here. So if I put 2 here, what does mean? C is 1, that's correct. Here we have 2O, but this side we have about, this is 4 O's, right? This is 2 and this is 2, so 4 O's. So to make 4 O's, I have to put 2 here. I've made 4 O's, so everything is balanced. Okay, but that's not, this wasn't a part of our equation, but yeah, just to give you a bonus, yeah, you know how to make an equation in case they tell you to make an equation I. So now the equation is not done. This at the last end I just, yeah, my paper is small because I have to match the camera size. So if I had spaced this side I could have included to say that the enthalpy change for this equation I. The enthalpy change for this equation is, don't forget, then use the word release. There's a word release here. So release, that means our enthalpy is negative 890. Yeah. So we have that kind of enthalpy change. It's negative. Why it's negative is because they said the word release. So don't forget our previous session. Yeah. So from here, what do we do next? So from here now, that we'd like to go to calculation I. They're telling us that calculate the enthalpy of this much of methane. So what are we going to do? So let's just start with the equation I. So the equation that we should know is that 1 more, they've told us 1 more I, 1 more, this is where the 1 more comes in. So 1 more of methane I, 1 more of methane, that is methane, CH4I. 1 more of methane is able to produce negative 890 kilojoules. What about the more that can be produced by these grams I? So that means I have to find the moles of these grams I. So let's try to find them before we come back to the equation. So that means I have to say the mole which is here, the mole for 5 grams I. The mole for 5 grams of methane should produce what we don't know, and then we cross multiply. But in this case, that means I first have to find the moles I, because this is in grams and this is in moles. So these two guys are not compatible. So let me change this in moles. To change this in moles, we have let me start with methane. So we know how to change I. We use it motion. Mole is equal to mass over Mr. Mass over Mr. That's what we use. Mole is equal to mass over Mr. But in this case, yeah, our mass is given, but we don't have Mr. Let's find first Mr. So to find Mr. So CH4. So H there is 1.008, 1.008, and then it is times in 4. Times 4, times 4. And then the C, carbon. So carbon uses 12.01, 12.01, which is just going to be times 1. So that is just going to be, oh, I've already put a cosine. So that's just going to be 12.01, and then for hydrogen here, it's going to be 4 times 1, 4 0, I should have started this side. 4 times 8, that should be 32. So that we have, I think we will have this. Yeah, we'll have this. 32 remainder shani, and then we'll have this. So so and then we add these two guys together to get our Mr. So Mr is equal to, we have this. What can we do? So 4 plus 12, 4 plus 12, that should lead us into the 16s. 16 point. So these two guys will give us 0.42. So that's our Mr. And then we now go to the mole. Mole is equal to, our mass is 5.9 grams, and our shan is, this is a point I. Our Mr is 16.42, and then we just do calculations. So to do calculations with this, let me try to use a calculator on this one. So calculator says when you have 5.9 divided by, what are we dividing by? We're dividing by 16.042. So we have that I. Let's just take it to 2 decimal places I. So we have 3.67i, 3.67. So we'll have 0.3. I said what? I said two decimal places, right? Two decimal places. So 0.367i, 37. Sorry, that should have been 37, not 367. Okay. So that is two decimal places. So now I go back to my equation here. So I have to put in that here there's 0.37. So we say that one more is giving us the negative 890 kilojoules. Right? So what about the 0.37? How is it going to give us? We don't know. We now cross multiply. We cross multiply. So we'll have x is equal to just 0. Shine times that guy. Yeah. Okay. Let's try to do that one. So 0.37 times negative. You know it's negative. Okay, it's negative. Just put it in the head. It's negative 890. Yeah, we have that 329.3. So negative 329. Okay, so the other thing was calorimetry, right? So calorimetry. Okay, so in calorimetry, here we're just talking about how heat is measured when we consider temperature in the system. So yeah, so calorimetry, I'm saying that this is where we measure heat, whereby we measure the temperature change. We measure heat, sorry. Yeah, considering the temperature changing, considering the temperature changes. So we can say that this is the science. This is the science of measuring heat. We're still measuring heat by considering, or we can say based on temperature change. So this temperature change, it can either be exothermic or endothermic, either absorption or release. So this is the temperature measuring is still the temperature of the system, and the energy or the heat we are measuring the temperature of the system, not the surrounding. Please get we stick to that one. So this is the science of measuring heat based on temperature changing. So the temperature changes in the system. Okay, so in this science we are going to look at two things on this topic of calorimetry. We're going to talk about two things. By the way, there's an instrument that is used to measure this change, to measure the same heat. In this case, we call it calorimeter. Let me just write it. An instrument known as what? Calorimeter. So calorimeter is used to measure heat changes or the heat when you are considering temperature. Okay, so in this case, I say that we're going to talk about two things in this calorimeter topic. So in calorimeter, we're going to talk about the heat capacity. Don't forget, when you hear the word capacity, that means you are talking about somewhere where there is something, either a limit, something about having a limit. So capacity, that means there should be a limit somewhere. Okay, so heat capacity, we're talking about the amount of heat needed, to increase the temperature of the system by 1 degree. Okay, so meaning there's a limit, meaning when we have little heat, you cannot increase the temperature, but when you have more heat, you are increasing. That's why there's capacity there. So let's just write that down. So I'm saying that this is the amount of heat, needed to increase the system, or the temperature, to increase the temperature of the system by 1 degree Celsius. So this is the amount of heat needed to increase the temperature of the system by 1 degree Celsius. Simple to define or simple to master. Okay, so this same heat capacity has a symbol Q, the same Q that we use when calculating internal energy. We say that internal energy is equal to Q plus Wi, the same Q. Yeah, so that's heat capacity. We also can go to the last one, the other one, which is the specific heat capacity. Specific heat capacity. So specific heat capacity. So in specific heat capacity, what do we talk about the most? In specific heat capacity, we are talking about the same amount. So don't forget, it's still capacity. So we're talking about the amount of heat needed. We're talking about the amount of heat needed to the amount of heat needed to increase the temperature, of the system. Sorry, let me just repeat that. Of 1 grams of the system. 1 grams of the system by 1 degree Celsius. Okay, so we're saying that specific heat capacity is the amount of heat needed to increase the temperature of the system, the temperature of 1 grams of the system by 1 degree Celsius. So that's how it goes. So let me just repeat it. Amount of heat needed to increase the temperature of 1 gram of the system by 1 degree Celsius. So that's why it's specific, because we're including the 1 degree Celsius. We have defined how many amount of the system we are dealing with here. That's why it's specific. So these two guys have some related equations. The Q and this one actually we use. So the specific heat capacity, you can find it SI. So it can have a symbol S. Sometimes it can have a symbol CI. That is, specific heat capacity. So you can find it with a symbol S or a symbol C. Okay, so in this case we're going to use the CI. In this case we're going to use the C. So there are some equations that involves it too. So to find Q, the equation for Q, we have equation Q is equal to we can say what? Q is equal to MC, the delta of Ti. So heat capacity is equal to mass times the specific heat capacity times what? Change in temperature. So change in temperature meaning you might have the difference. So the two temperatures, you find the difference between the temperature of reactant product minus temperature of reactant. C is equal to, C, don't forget, is specific heat capacity. Specific heat capacity is equal to QI, which is heat capacity over change in temperature. So I can see one thing that is common here. Change in temperature is everywhere. So is it almost like making this a subject of formula? Okay, so this is the question we are given. Which was like one of the most tough questions that I've seen so far in this topic. So this question was saying 3 grams sample of glucose is replaced in the bomb calorimeter and filled with oxygen under pressure. The calorimeter is filled with 1.2 kilograms of water. The initial temperature is 19 degrees Celsius. The reactant causes the temperature to increase to 25.5 degrees Celsius. The heat capacity of the calorimeter is 2.21 kilojoules per Celsius. So that means that is the heat capacity. That is heat capacity. So the molecular weight of glucose is 18 newtons. Taking heat capacity of water as 4.18 kilojoules per grams. how much heat is dissolved by combustion of 1 mole of glucose. So 1 mole of glucose. So this is talking about 1 mole of glucose and gives us many information. So glucose, oxygen is added, and also water is added. Yeah, water has its own calorimeter, or has its own capacity, and also the others. So how do you answer that one? So the first thing, let me just put this one close because I think I need it. So I think the first thing here we're going to do is to gather up all the needed the total heat capacity in this system. So in this system we have heat capacity of the calorimeter. So the calorimeter gives us the heat capacity of 2.21 kilojoules per degree Celsius, and then the water also gives us its own heat capacity of 4.1. Is it 4.1? Yeah, 4.18 kilojoules per grams. And then all these two guys, this one has a mass, has its own mass of 1.2 kg. So I think I have to find the total heat capacity in the system. Okay, I need to find the total heat capacity in the system. My calorimeter is giving that, water is giving that. So the total heat capacity in the system. So, the total heat capacity in the system. So first of all, I have to make sure I have to change this. The grams has to be cancelled so that it remain only Celsius. So let's do that. So we're going to say for the water, the heat capacity of the water without including the grams. Including the grams that we have, the mass that we have, we are going to have 4 calorimeter, or 4 kg, kg per grams, per grams, times we have that 1.2 kg. Now since this is in grams and this is in kg, that means I have to convert this into kg, and that means I'm going to multiply by 100. So it's going to be 4.18 kg time over grams, because it's per grams, times 1.2, which is times also what, 1,000, 1,000, 1,000. So everything together, that should give us about, so let's say we have 4.1. Come on, why things going like this? Come on, I cannot repeat. So the first thing to do there is always we have to sum up the sum. We have to sum up to find the total heat capacity in the system. So being given, we know that the heat capacity of the calorimeter, calorimeter has its own heat capacity, which is 2.21, which is kJ per Celsius. And then water also has its own calorimeter heat capacity. So water has its own heat capacity, which is 4.18 kJ per grams. So, and also we know that water has been given the mass of 1.2 kg. Okay, so to find the total in the system, I first have to, let me make this one into, let me first change this one. I've seen that this is per kg and this is per Celsius, but I can cancel it by using this kg, or per grams, and this is per Celsius. So I need to cancel this. So I can say that 4.8 grams, 8 kg, kg per gram. Since it's per, I can say over gi, over j, times 1.2 kg. So that this can cancel with this, but this is in kg and this is in grams, so I have to change this in grams. That means I'm going to multiply with 3 to the power 8, 10 to the power 3 grams. Yeah, that should kill this guy. That should kill this guy. So when I multiply everything here, I should have, so we have 4.18 times 2 point, is it, yeah, 2.4, is it 4? 2.2 or 1.2, sorry, yeah, 1.2 times the 100, times the 1000, sorry, times the 1000. I'm having 5.016, but I can just get that as 5. I mean, I don't have to go far. So I will get the answer for calorimeter or for Shan. That is just for yeah, that is for, yeah, let me just get it. So for water now, water has the capacity of 5.061. So since it has this heat capacity, we're going to convert it with the other one, to add it with the other one to get the total heat capacity in this system. The total heat capacity in this system, we're going to say is equal to 2.21, which is kj, sorry, even this is kj. So kj times this other one, 2.5, not plus, not times, it's plus, because we're just adding them. So kj plus 5 point, I can just round it off so that they can match. So make it 5.02 kj also. So this should give us about, is it 7 point something, say 7. So let me just add. Okay, yeah, this is, yeah, 7.23. This should be 7.23 kj. So this is the total in the system. So now they're telling us to find what is in the thing. So now, according to our data, not to go far, we can use the more concept, or we can use this other concept. But yeah, let's try to find the glucose. The glucose in the system. The glucose in the system, as we are told, it is 3 grams. But they're telling us to find for 1 more. They're telling us to find for 1 more. So that means I have to, yeah, work out these things. So how am I going to work them out? So first of all, since this, I'm going to find the moles of this which are producing this much joules, which are producing this much energy, or this much heat. So 3 glucose is C6H12 or 6. So let me find its Mr. first of all, and find its the real moles for this guy. So it should be 12.01 times 6. This should be 1.008 times 12. This should be, is it 1 again? 1.00, no, sorry, this is 12. 12 times 6, 12.01. Okay, I will just write on the calculator. So this is 12.01 times 6. Okay, so the first one, 12.01 times 6 again. Wait, how is it? This is supposed to be 16, sorry. This is 16, this is 16. This is 16. Okay, so we have 16 times 6, which is giving us 96. And then we have 1.008 times, is it 12? Which should just be 12. Yeah, so it is 12.096. And then the last one, which was 12.01 times 6. That is giving us 72.06. So if I add 72.06 times 12.096 times plus 96, together we're having 180. That is 180. Let me make it 1.6. So that's the mister. So if we're having this as a mister, we can now say the mole is equal to 3 grams over this mister. So 180.16. So you can say 3. I'll just say divide by answer, since My answer is already there. So it's going to give me 0.06. That number is long. So 0.06, let me just say 0.017i. So we're going to get 0.017. Okay, so we have 0.017. So yeah, to find the heat capacity in here, we can say heat capacity is equal to, since we already used mass I, there was mass, we used the mass, so we can just use the other way. We can say it's the other way I. So we're going to say mass is already being used, so we can just say C times this I. So mass has been used. I don't forget what we used. We said the 1.2 mass I was used, so we can just say. So what has remained is the specific heat capacity times the change in temperature times the change in temperature. So our specific heat capacity is that number that we had at first, because we were doing it with grams, with grams. That's why the mass was included. So where is it? Yeah, that was 7.23 kilojoules. So this kilojoules is going to be multiplied with the time I. Now the temperature. So the temperature, our temperature, we had the first one, which was 25.5 minus 19i. 25.5 minus 19. So that on the calculator, so we have 7.23 times 25.5 minus 19. So that's going to give us, for the everything together, the calorimeter here, or the heat capacity is 46.999. So that one, if you try to round it off in any way, it's going to give us just 47. Let me just say 47.0. So 47.0, that is still in kilojoules. So this is the heat capacity we're working with right now. Yeah, so this being the heat capacity now. So don't forget, the heat capacity can also be, we said that heat capacity can also be the HI. What's H again? The enthalpy, the enthalpy. So okay, so since we can say that this is the enthalpy, what does it say? This was released, it was released. Was it released? But it's never gotten to be negative, meaning it was gained. Okay, 0.17i is giving us how many joules? Those are joules. What's 47.0 joules, kilojoules. And then for one more, which we don't know. So if we cross multiply here, we're going to have things like this. X is equal to 47.0 kilojoules over 0.017i. So 47 divided by 0.017 kilojoules, that is going to give us 2.76 kilojoules. So this was the amount for glucose. Another example, example 5, just remaining one more example and we are done. Okay, but I think the last example, yeah, need to be exercise. So in this question, is saying determine the specific heat of the sample of copper from the fact that 64 joules are needed to raise the temperature of that is 5 Q5i. What's that? That is 15 grams of copper from 22 degrees Celsius to 32 degrees Celsius. So how are we going to solve this? So they are telling us to find the specific heat capacity, and specific heat capacity is using the letter CI, the letter C. So since we have grams in here, I think the best formula to use, I'm going to derive the specific heat capacity from this formula. So heat capacity is equal to mass times specific heat capacity times the difference in temperature. So in this case, what am I going to do? I'm going to say that I'm going to make C the subject of the formula. If I make C the subject of the formula, that means C will be alone here, and it will be Q over M delta Ti delta T. So everything is already there. I've not seen anything to convert to any other thing. So everything is just okay. So all I'll do is to say, so C is equal to 64 joules over our mass is 15, and then temperature is, so we're going to say temperature 2 minus temperature 1. So 32 minus 30, 22, 22. So I'm sure that is 10. I'm sure that is 10 there. So we have C is equal to, just to use the calculator in the exam, there's no need of going step by step. So to use the calculator in this form, we have 64 on top, 64 divide by, I'll put it in bracket, 15 times, I said 10, so that's going to give me 0.42, 0.4, I'll make it 6, I'll make it 3, so it's to just round it off. So this is the joules. So this is the heat capacity per 1 mole. Don't forget this is heat capacity, so meaning per mole, per Celsius, per gram. This is the last question, which reads, a 50-gram sample of water at 100 degrees Celsius was placed in an insulated cup. 25.3 grams of zinc at 25 degrees Celsius was added. The temperature dropped to 18 degrees Celsius. What is the specific heat capacity of zinc? So what is the specific heat capacity of zinc? Okay, I think this one should be, I think you can answer this on your own. Try